Today I'll be going through a notebook demonstration of what pipeline processing of MOS data will look like. I'll take you through a worked example using a simulated data of a simulated scene, taking you through stage 2 and stage 3 of the pipeline, what the pipeline products that those generate look like, and then what are some of the options for reprocessing. In particular, at the end, I'll go through an alternate mode of background subtraction methodology, just to show you what that might look like. So to start off, if you go double click on the file called JWebbinar 7 _ NIRSpec MOS, that should bring up this notebook here. Okay, so we'll just be taking you through step by step. So as we go through the different cells, remember just do a shift enter to proceed to the next cell. So by introduction, I covered some of this already. I note that for this bigger demonstration, I'm using the pipeline version 1.2.3, which is the latest stable release of the pipeline. There are some caveats to be aware of for this. If you do go through this on your own, if you happen to use a different version of the pipeline, you may see results slightly different. Just keep in mind that, of course, the pipeline is undergoing continuous development, and so there are always changes, tweaks, and advances being made to the capabilities there. One other thing to note is all of the processing that's done by the pipeline, the various steps to apply various corrections to the data, are based on calibration reference files. Now, of course, we're not actually in space yet, so a lot of these files we can't really get actual calibrations until we get on orbit and can observe standard stars, for example, for flux calibration. And so those files are either, in many cases, placeholders with no real information, or are rough versions of what we expect to get on orbit based on ground data. And so the upshot there is just keep that in mind when you're looking at the results that I'll be taking you through today. In particular, do not take any of the flux information that you will see as indicative of what you should see in actual flight data. So as I said, the demonstration will be using a set of simulated data. These data were generated by the ESA team's Instrument Performance Simulator, or IPS. In this case, the simulations were created using an input scene that consists of 60 point sources located within a single MSA field of view, each of which is described by an emission line galaxy template spectrum, but put at different redshifts. So you'll see in these cases, if you go through all of the spectra in turn, you should see the same emission line spectrum, but the wavelengths of the lines will shift because they were put at different redshifts. The observation itself, to create this simulation, basically included an MSA configuration where a slitlet was open on each source in the scene. Each slitlet consists of 3 open shutters, one containing the source, and that changes depending on which of the 3 exposures you're looking at, and then 2 other shutters in the contiguous slitlet open on background. So the simulation includes both a source flux and background flux, as well as a treatment of the noise. And finally, there's a set of 3 exposures total to simulate knotted exposures, as is the standard observing configuration for point sources, where each source is moved successively into each of the 3 shutters in the slitlet, done primarily to facilitate background subtraction. the instrument was configured in these simulations with two different disperser settings, the G235M and G395M gratings. Those are the medium resolution or are of about 1000 resolution gratings. I have renamed the files for convenience so that you can better see what they're reflective of in terms of which of the node positions each is considering, as well as the instrument configuration. Note that that's not the naming scheme that you will see when you actually see real data products available in the archive when you get real observations. As with the pipeline, there are a number of caveats to be aware of for the simulation, some limitations in the simulations. I won't go through all of these, you can read on your own, but basically, in particular, the IPS doesn't include a full treatment of all the throughput-related effects that the pipeline, stage 2 pipeline treats. So again, this basically means the flux information that you'll see, again, should not be taken as indicative of actual flight performance. One thing I wanted to note in this particular case is this particular set of simulated data is preliminary. There are some issues that are being looked at. They'll eventually be replaced by a newer set in the near future. Though that's going to happen, of course, after this webinar takes place. So we ask that you not share the data with anyone outside of the context of this webinar. Once those data are updated, we will let you know. So anyway, let's get into it. So we'll start with the first few cells that will import all the packages that we need to look at the data, run the pipeline, and look at some of the associated metadata and other files that are related to that. So we'll import some packages we need for that, including AstroPy visualization, Matplotlib we'll be using for showing the data products. And then the third cell here imports all of the pipeline modules, both the stage and individual steps, even though I won't be taking you through individual steps today. Now some convenience functions. So we can't actually do the processing in real time here. It takes a fair amount of time to go through all the processing steps, particularly for the JWST 2 pipeline, particularly for MOS data, because we're working with quite a large number of sources, about 60 in this case. And with the gratings, as Tim mentioned, it covers a fair amount of real estate on the detectors, so that's a lot of pixels that need to be calibrated. So that takes far too much time for us to do in real time. So what I've done is pre-computed all of the data products for the stage 2 and stage 3 pipelines first, and so those have been placed on a shared directory here. So this cell will set a link output dir parameter that will link to the location of the data, and that will use that in subsequent cells when we display the results. The next cell is just a plotting function. And then next, I put a processing flag here. So as I said, we can't do this in real time. But yeah, I want to show cells that show you how you would actually run the different stages of the pipeline. And so in order to skip those for the webinar, I've set this flag equal to false. So all the cells that actually run the pipeline will be skipped over. If you want to go back on your own and rerun and see what that actually looks like, just change that flag to true, and then you can run the various pipeline run cells. Just be prepared to wait for a while. It can take, I think, roughly half an hour or so to run through all three exposures through the Spec 2 pipeline. So now, as I mentioned, using input simulated data, one of the limitations of the simulations is that, in general, we don't simulate raw level 1B up the ramp data. So we can't start the pipeline processing from the beginning, at stage 1. The products that we get from the simulator are the equivalent to level 2A data or count rate images that we've then converted to pipelinable format. So when we actually do the pipeline processing, we'll be starting at stage 2. So here, just to show you what the inputs look like, these are the count rate level 2A files for one of the 3 exposures. So this is the D1 exposure, or the NOD exposure, where the source is placed in the central shutter of the 3-shutter slitlet. And this just shows what that exposure looks like for both the NRS1 detector. So this shows the sort of the shorter wavelength end of the spectra here. So you see all of these wider traces here are the slitlets that were commanded open to observe the sources of interest. You see a few of these narrower traces, like this one here. That's, as Tim mentioned, there are a small number of shutters that are stuck open, so they're always open to sky. And you're seeing here is the sky background emission being transmitted and dispersed onto the detector through those failed open shutters. Also, we get fixed slit data for free with all MOS data. As Tim mentioned, the MOS spectra are dispersed on the detector sort of in this top and bottom regions here. And in the middle are data from fixlets, which are always open to sky. In this case, what you're seeing is just background emission being transmitted through those slits. And then here is the same thing, but for the NRS2 detector, now showing the longer wavelength piece of all of these spectra. And then here is a zoom in of this exposure for the NRS1 detector, just showing you a little bit more detail of what this looks like. So again, we've opened a 3-shutter slitlet on each of our sources of interest. Here is one example here where you see the source trace, the continuum, and actually a few of the emission lines here visible for the source placed in the central shutter of the 3-shutter slitlet. And then you can see it's a little bit noisy because the background emission in this case, because we're using gratings, is not very strong. But you can see here the background through the top and bottom shutters of the 3-shutter slitlet. And then a similar case up here, but in this case, the source is so faint that you don't actually see it above the background. And then the narrower trace you see up at the top is one of those failed open shutters. So now let's look at some of the associated files that are used to help process the data. So first of all, when we do the pipeline runs, we'll be specifying the input files using association files. So these are typically generated automatically by the pipeline for an exposure set that it knows need to be associated together. For example, in this case, we have 3 exposures where the sources have been knotted in the 3-shutter slitlet. The pipeline is able to identify that set of exposures, knows that those were intended to be associated together, particularly for the purpose of background nod subtraction. And so it constructs an association file which lists all of the exposures that need to be associated. And that's what's used to specify the inputs to first the spec2 pipeline. Okay, so the association file that we're using for this processing run here, since all of this has to be generated by hand because we're not doing a full end-to-end processing, this particular file was generated by hand. This just basically shows you what these association files would look like. So here we list all of the input exposures here for the G235M grading data. So again, the D1 here and then D2, D3 are the 3 knotted exposures. We're using all of the rate files, level 2A files as inputs here. And then, so each of these input files is specified as an input product. And then we also have a set of background exposures to be used as backgrounds for the node subtraction in this case. So that's basically the other two exposures in the node set. And so the pipeline, when it reaches the background subtraction step of the spec2 pipeline, it will know to take those two associated exposures, average them together, and then subtract them from the science spectrum input to do that. And then it goes through the same process for all 6 of these exposures for both detectors. So it's a total of all 3 exposures for both detectors, a total of 6 files that are included as inputs. So a unique aspect of MOS data, because we have multiple targets that are dispersed on the detectors, and the location of the spectral traces depends on which shutters were actually opened on the targets. The pipeline needs a way of tracking all that information. And we do that by using what's called an MSA meta file that the pipeline generates using data that it takes from the PPS database. And that data is populated for the most part when you design your observations in the MSA planning tool. It's various information such as the specific location of the shutters that were opened in each slitlet, which shutter contains the source for a particular exposure, the position of the source within its shutter, information like that is required in order to do the processing of the spectra in the spec2 pipeline. So I'm going to show you what one of these metafiles looks like. This is the metafile that we generated by hand to go along with this particular set of simulated data. So the metafile contains essentially 2 fits binary tables, one called shutter info and one called source info. So shutter info, here's the set of columns that are present there. That contains all of the information related to the shutters that were open for each of the slitlets. So there are columns that contain the unique ID of each slitlet, an MSA metadata ID, which is essentially the same number for everything for a particular metafile. The location of each of the open shutters in the slitlets, so that's characterized by the shutter quadrant, the shutter row, and shutter column. There's a unique source ID that matches the slitlet with the source that was placed in the slitlet. There's a background status, which basically tells the pipeline whether that shutter was open to sky background or actually contains the source. The shutter state, whether it was open or closed. Estimated source in shutter X and Y gives the position of the source if it's contained in that particular shutter in both the X and Y or dispersion and cross dispersion directions in relative units, where 0, 0 is the center of the shutter. Dither point index, which basically connects a particular shutter and slitlet with the exposure number within the set of exposures that are associated together in the observation. And then primary source, that's the basically the complement of background. That's basically tells you whether the source is included within that particular shutter or not. So here, just to show you what this looks like, here are the first 18 rows for this particular metafile. And so this is showing you the first 2 slitlets. So you see here, some of these rows are repeated because in this particular case, we have a set of 3 knotted exposures. And so each shutter in this slitlet, as you can see here, those shutters have this location here, quadrant 1, row 294, column 46, 47, and 48. Each of those is repeated 3 times because this represents the 3 different exposures. So, for example, the top shutter in the slitlet contained the source, as indicated here, in the second of the 3 exposures, and so on and so forth for all of the different shutters in that particular slitlet. And then here we have the second slitlet here with ID 2 containing a different source with a different set of shutters commanded open. So again, this is all information that the pipeline needs in order to apply various calibration. The next table is the source info table, which contains information specific to each of the sources as identified in the shutter info table by the source ID, which is this column here. This contains information such as, again, the source ID so that they can be matched, the name of the source, if that's different from source ID, that's taken from the catalog that was used to plan the observations, if there was an alias included, and then the source RA and det coordinates on the sky. Pre-image ID points to a pre-image exposure if that was taken. And then stellarity is a parameter indicating whether the source is a point source or extended, because we have two different processing flows depending on those two cases. And then here is the first 10 rows for that table in this meta file, again, just showing you all the info. So, and then a little bit later on, I'll show you one example of how to interact with this table and edit it to do certain reprocessing of the data. In general, you wouldn't want to change any of the actual values of these data. You have to be careful with this because they actually have quite a large effect on how the data are processed. But if you wanted to edit the file, for example, to remove certain shutters that may be contaminated, you could do that simply by editing the table and removing those rows. And again, I'll show you an example of that later on. So let's move on to running the pipeline. So again, here I've set this run flag. So because we've set it to false at the beginning, this will be skipped over. But if you want to run this offline, simply set that flag to false, and you'll run. So this is basically the specifications you need to actually run that pipeline and save the products that it generates to an output directory. And then if you were to run that for real, this is what the data products will look like. So we're going to go through, I'm going to only show you one example. There's, of course, 60 sources included in this particular data set. You can actually, if you want offline, loop through and look at all 60 of them if you want. But because that takes some time and is a little bit confusing to look at, in this particular example, I'm just limiting it to one particular source that's included here. But this cell is basically opening all of the data products. The primary data product is the calibrated, unrectified 2D spectra, or the underscore cal.fits file. And then there's also other products that are intended as quick look at the exposure level. That's the rectified 2D or S2D product, and then the 1D extracted spec for X1D. So this will loop through all three of those files, and then within each one, we'll then loop through all of the different slitlets that were extracted from the data. And so here, again, I'm just going to show you one case. So this is for slitlet number 31. So here you can see, here is the cal.fits product for this particular slitlet. So you can see, because when we ran the spec2 pipeline, we used the association file, which included the background associations, the background step in spec2, averaged those backgrounds together and then subtracted them from the science exposure. And you can see the result here, this characteristic positive and negative traces. In this particular exposure, the first exposure in the node set, the source is located in the central shutter of the slitlet. And here you can clearly see the continuum as well as some of the emission lines of that source with this positive trace here. And then the negative traces, that's a byproduct of the node subtraction you can see at the top and bottom. And then for the same source, here is the quick look rectified 2D spectrum here, where now the pipeline has resampled that spectrum onto a regular grid in wavelength and sky coordinates. And then the 1D spectrum, which basically is an aperture extraction of this rectified data, or it opens I think the default is a 6-pixel wide aperture centered at the trace of the source, which that centering is based on the source coordinates that are specified in the meta file, and then sums everything up along wavelength bins. And here you can see the example in this case of the 1D spectrum. And then subsequently, we're looping through all the exposures for both detectors. Here's the first exposure with the spectrum on the NRS2 detector. Since in this particular case, most of the spectrum was located on NRS1, there's just a short piece to extract on NRS2 that you can see here. Here's the same thing, the calibrated unrectified spectrum here, the rectified 2D spectrum here, and then the extracted 1D spectrum from that. So then just going through the rest of this, this is the second exposure in this series where you can see now the source is moved down to the bottom shutter in the slitlet. Again, the positive trace there, and then the 2 negative traces from the background subtraction, and then the same quick look products for that. Same thing for the NRS2 detector. And then finally, the third exposure where the source has been moved to the top shutter. The same quick look products for that. And then again, if you were to do the loop through everything, you would see the same set of data for all of the other sources that were contained in each exposure. Okay, next, some files. So we have another grading in this set that I'm not going to take you through in detail here, but I just have this here and processed that part of the data. I will show you a little bit later one way of combining together multiple gradings. So that's just the cell to process that data in preparation for that. Now we'll go to the Spec3 pipeline. So now that we've processed all of the individual exposures, now in this data set, we basically want to combine all of those exposures together to improve the signal to noise of the final extracted spectra. And that's what happens with the Spec3 pipeline. So the first cell here is actually a way of generating an association file manually by using all of the underscore cal.fits files, the main product from the Spec2 pipeline run, and basically putting together an association file that includes all of those files. And actually, I didn't show what that looks like, but basically it's similar to what I showed above for the Spec2 association file, but it's simply just a list of, in this case, a total of 6 files. So 3 exposures, 2 files for each, 1 file for each of the 2 detectors. All of that will get combined together by the Spec3 pipeline. And for MOS data, essentially what happens is the pipeline will actually go through each of the individual exposures and reorganize the data from an exposure level organization that's the inputs, basically the cal.fits files. I should have mentioned earlier, the structure of those files is such that there are multiple extensions for each of the slitlets that were extracted and processed. So at the beginning of Spec3, the pipeline will go through and reorganize everything and basically create a single file for each source or sort of slitlet. And then there will be multiple extensions with all of the exposures that included that source. And then all of the actual processing done by the Spec3 pipeline is then done on a source-by-source basis. And that includes some steps such as the outlier detection that I mentioned. In this case, we're skipping this particular step in order for that step to run and produce good results, we have to have accurate, robust noise information. And for various reasons, the simulated data that we're using for this demonstration doesn't have that. And so you won't get good results with that. So we're going to skip that step in this example. This shows you an example also of how you would actually do that when running a pipeline. Okay, so assume we had run that. Here is what the products look like. So this, I'm just showing here, one source is the same source that we looked at exposure level from the Spec 2 products. If you want to look at any of the other sources or all of them in this loop, simply comment this out or change the slitlet name that's specified here. And so here I am showing the final combined rectified 2D spectrum is shown here for this particular source. So here, not you should see the positive and negative traces, since everything has basically been shifted to overlap. You would normally see, in this case, two negative traces on the top and bottom. There's actually a known issue with how the data are projected to the output grid that's causing a shift here. So it's cutting off the lower negative trace. But that really doesn't matter because the full positive trace, which is really what we want from this, is fully included here. And then finally, the ultimate product, at least for point sources at level 3, is the final 1D extracted spectrum from this combined 2D spectrum, and that's what's shown here. So now you can see here all 3 exposures now have been combined. Both detectors have also been combined, so we see the full wavelength range that's available with this particular grading, the G235M grading. And you can see here there's a gap here with no information. That's basically the gap between the 2 detectors where we can't recover any information from that. But we see the 2 pieces from the 2 detectors here. So depending on exactly which shutter was open for that target, you would see this gap at different wavelength ranges for different cases. And then next is the same thing for the G395M data. So now I'll show you the combined product there. It's very similar, but now we're seeing this is the longest wavelength grading, medium resolution grading. So you see the similar data from through a 3 to 5 micron range. Now I'll just show you really quick. Here's an example of now that if you have data like this where you have extracted spectra for multiple gradings with the same resolution, this is one way you would combine those together. There's an alternate pipeline step that will combine 1D data, and this just shows you how you would do that using an association file which lists all of the 1D spectra we want to include. In this case, there's just 2 of them for G235M and G395M. And so this would run that particular step to combine them together. And then here is the result for that for this particular source, showing now the full range that you get for these 2 gradings, basically 1.7 to 5 over 5 microns. Okay, so that's the basic run for stage 2 and stage 3. Now to end, I wanted to show an example of this alternate background subtraction method, which is master background. So as we mentioned earlier, when you have extended sources where you don't want to do the node subtraction because of source overlap, this is the methodology that you would want to use. The normal use case for this is when you design your observations in MPT, if you know ahead of time that most, if not all, of your sources are going to be extended and you want to use this methodology, you would generate your plan accordingly, where you would open slitlets on each of the sources but then also open individual dedicated slitlets of one or more shutters each that are open only onto Sky. When that happens, there is metadata that's passed down to the pipeline that tells it that those particular shutters are intended for background only. That's indicated in the MSA meta file. And then the pipeline will identify that and know that it will need to process those as backgrounds, create a master background from that, and then apply that to subtract the background from each of the source spectra in turn. In this case, because the simulations were generated with the nod subtraction use case, there were no dedicated background shutters open. However, in many cases, the source that was used in some of the shutters is really not visible over the background, so we can use those as proxies as if they were meant to be open purely to background. And so I'm going to take you through a process of we're going to go through that original meta file and isolate just a few that we want to do for this process. So first, we're going to go through, and so that we have a comparison, we're going to first process the data for one exposure with just one source without any background subtraction. And so here I'm taking that original meta file, I'm isolating just one row that contains source from slit 31 that's a reasonably bright source. And I'm going to create a new meta file with just that row. And that's what's done here in this meta file. And here's what the shutter info table looks like. In this case, just one row, this slit 31, just one shutter that contains this particular source for this particular exposure, the first exposure in the original nod set. Then we're going to copy the original data files so that we don't overwrite any of the products, and then rerun them through the spec2 pipeline. So now, because we only have one line in the meta file and working only with one exposure, the pipeline won't do any background subtraction. And so we'll have a comparison data set to look at. The next cell we'll go back and do the same thing from the original meta file, but this time including a number of shutters open to background. And I've already gone through and looked at all of the different slitlets in the original set, identified which ones have no obvious sources, and picked out shutters from that that I'm now going to identify as background shutters. And that's all of the row indices here like this. So I'm just going to reconstruct this table using only these rows. For the shutters that I want to use as background only, I'm then changing the background and source, primary source status columns to these appropriate values. So background yes, source no, and that's what will tell the pipeline that those slitlets are meant as backgrounds. And save that to a new meta file. Here's what this looks like. So we have our source slitlet here, 31. Again, all these are just single shutter slitlets in this case. And then everything else I've set, these are all different slitlets now, as evidenced by their different slitlet IDs. And then they're all open on background. Now again, I'm going to copy the original rate files so that we won't overwrite anything. And now we'll rerun spec2. So here, what happens here is now different than from what we've done previously. So as I said, because of how we've set up the meta file, the pipeline will identify that there are background dedicated slitlets. What it will do then is take those background slitlets and process them first, calibrate them as an extended source. If there are multiple background slitlets, which we have in this case, as we've identified a number of them, the pipeline will go through, process each one in turn, extract 1D spectra from each, average those together to create a single master background spectrum with higher signal to noise. Then it will go back through, and for each source slitlet identified in the meta file, in this case we only have one, it will do all of the processing steps in the spec2 pipeline up to the master background subtraction step, which includes these steps here. Once it gets to that step, it will then go and take the 1D master background resample it into the 2D space of the source spectrum, subtract that pixel by pixel to remove the background, and then it will proceed with the remaining steps in Spec 2 to generate the final calibrated background subtracted spectrum. So it's a little bit of a complicated process, particularly for MOS. But here's where we will actually run the Spec 2 pipeline in this case. And here are the results that come out of that process. So again, here, this is just going to be the single exposure, just one source. That's the only one that we identified in the meta file. First, we'll actually see when you actually run this, you have the option of outputting the master background to a separate file so that you can actually look and assess that the quality is what you want for that. So here is the result. So this is the averaged background for all of those shutters that we identified as backgrounds, the 1D spectrum. And then here shows you the 2D resampled master background spectrum. We're taking this 1D, resampling it into the 2D space of the source. And then this is what's subtracted from the source 2D spectrum. Here is the final background subtracted calibrated spectrum of the source. Here's the rectified 2D, and then the extracted 1D spectrum. And then just to wrap this up, the final cell here now compares the final extracted 1D spectra for all of these cases that we've done. The blue is the result from the processing that we did without any background subtraction. Then the first panel here shows in orange what that extracted spectrum looks like from the node subtracted exposure. And then here is the 1D spectrum from the master background subtracted spectrum. As you can see, these two are consistent in flux level. The noise level is a little bit lower in this case because we've averaged together multiple backgrounds. You get a little bit better of a result in that case.